Hey guys, welcome to Chapter 2 lecture. I'm going to go ahead and get the screen share set up. Okay, so at this point, I'm hoping that you can see uh, myself and you can see the um, slides here. Okay, so in this lecture, we're going to talk about physical systems. We're going to go over matter, energy, and geology. And we're essentially going to do a crash course in chemistry and in biology. And hopefully at the end of it, you can sort of start getting some ideas about uh, how the world works from all the way from the finest subatomic particles through to sort of macro systems like you and myself. Okay, so let's see here. I'm going to skip over lecture objectives and general lecture objectives. These are good study tools. And I'm just going to start off with putting this lecture into a real life context. Okay, so what is the legacy of Fukushima? You may have heard of the Fukushima nuclear tragedy. Essentially, what happened in 2011 is that a major earthquake came through and created this giant tsunami. So the ocean shifted, it created a tidal wave that essentially went over a retention wall, and it flooded this nuclear power plant, uh, killing the emergency generators that were designed to cool the plant, and it overheated and exploded. Here's a photo of this. This was a massive disaster, super tragic. But for now, we're just going to focus on the nuclear fallout issue. So essentially, like I said, the backup generators were flooded. Cooling of the system stopped happening, and the nuclear reaction, which is sort of a runaway reaction, started to get hotter and hotter and hotter until things exploded. Okay, and so your book has this figure here, and what it's showing you is that there were 4 out of the 6 total reactors exploded, and created this nuclear meltdown. It was not good, but what we're going to do is take this example of nuclear meltdown and relate it to chemistry and relate it to the principles in this class that we're trying to talk about in terms of understanding the environment and how chemistry and matter interact with our environment. Another really, really good series put out by HBO, if you're looking for a new show, totally binge-worthy, is the show Chernobyl, about a different nuclear reaction. So good television there. Go watch it, I would suggest. So again, understanding these nuclear disasters like Fukushima and Chernobyl require knowledge of the basic properties of matter, energy, and chemistry. And that's why we're going to talk about it in this class starting now. So matter is defined as any material that has mass and occupies space. That's what the definition of matter is. And chemistry is just the study of these interactions. And now we're going to start this off with this idea of the law of the conservation of matter. I'm going to put myself down here. The law of the conservation of matter states that matter cannot be transformed from one type of substance to another, or it can be transformed from one substance to another, but it cannot be created or destroyed. So in ecosystems, matter is constantly cycling. Undesirable matter like nuclear waste or pollution, you can't destroy it. You can change it from one substance to another, but you can't just destroy it. You can't get rid of matter. The world has a fixed amount of material. So our planet has a certain amount of material, and it's only going through cycles. There's no new stuff coming in, and there's no stuff going out, for the most part. Maybe some very, very small introductions via like asteroids and whatnot. But for the most part, we have everything that's on the planet, everything that you see right now is all from the same amount of fixed material, which is pretty mind-blowing when you think about it. And you might hear people talk about, breathing the same air as dinosaurs. Well, that's true. The air that you're breathing right now could have been breathed in by a T-Rex millions and millions of years ago, because that carbon dioxide, that oxygen that you're breathing in, that has only gone through cycles in our planet. This is going to be a theme in our class of cycling, right? So this is the carbon cycle here. You don't need to memorize this figure for right now, but the point is that carbon is cycling into the air. It can be cycled into our bodies. It can be cycled into plants, and it just continues this really long loop. Okay. So atoms. This is the first of 11 slides on atoms and sort of the elemental nature and the building block nature of atoms and elements. So nuclear reactors, bringing this back to our nuclear disaster issue, use an element called uranium to power their reactors. And now uranium is one of these elements that you can find on the periodic table. Elements, by definition, are substances with specific properties that cannot be broken down further. So, for example, a sodium element, you can't chop that down and still get the properties of sodium any further, okay? Elements are organized according to their properties and behavior on the periodic table. I'm sure you've all seen the periodic table. And we're going to talk about the periodic table in a second. For now, I want to talk about the most abundant elements on Earth. So in total, on Earth, oxygen, hydrogen, silicon, nitrogen, and carbon make up the most abundant elements. That's mostly what our Earth is made of. But when you break it down into various parts of the Earth, including the Earth's crust or the oceans, as you can see here, you start getting different ratios of the abundance, relative abundance. And when you go to things like organisms, we're talking about, plants, animals, you, me. We're mostly made up of oxygen, primarily because we're water-based, right? H2O. But the next element down is carbon. We got a lot of carbon in our bodies, and as do all living things. Okay, so atoms and elements are chemical building blocks. Atoms are the smallest units that still have all of the elements' chemical properties. Atoms are made up of 3 subatomic particles. Okay, subatomic meaning below or smaller than atoms. Protons, neutrons, and electrons. Those are the 3 subatomic particles we're going to talk about. Protons have a positive charge, and they determine an element's atomic number. We'll go deeper into that in a minute. Neutrons have no charge. Neutrons sound like neutral, right? Neutral, no charge. And then electrons have a negative charge, okay? So protons, positive charge, electrons, negative charge, and in the middle you have neutrons, no charge. And just a nerd out alert here at the bottom, there are weirder, smaller, stranger subatomic particles that are outside of this course, but if you want to get into that, there's some crazy science going on right now. But right now we're just going to focus on these 3 subatomic particles. Protons and neutrons are found within the dense center of an atom called the nucleus. Okay, so the nucleus of an atom, not to be confused with the nucleus of a cell, same word, different meaning. Nucleus of an atom is in the center here, and the nucleus consists of protons and neutrons. Okay, and so an element's mass number is determined by its number of protons and neutrons, and you can find the mass number on the periodic table, and we will look over that in just a minute. But for now, what we'll see is that you've got this central nucleus consisting of protons and neutrons, and on the outside you have these electrons, and they orbit that nucleus. Okay, so carbon has an atomic number or a mass number of 6. Okay, and what that means is that in the center there's 6 protons, which are met with 6 neutrons. Neutrons are neutral in charge. And then in order to counteract the 6 proton positive charge that you have, you need 6 electrons. So a stable carbon atom has 6 protons, 6 neutrons, and 6 electrons. And you can find that information on the periodic table by just looking at its atomic number. Similarly, nitrogen, 7 protons, 7 neutrons, 7 electrons. Oxygen has 8 of each, okay? So atoms of the same element always have the same number of protons. Protons define the element, okay? So 1 proton is a hydrogen atom, and then you just keep going down the periodic table. Helium has 2, etc. And we'll look at the periodic table in just a second. Now, a proton defines the element, but the number of electrons can change, and when that happens, you create what's called an ion. And this is down here in this section here of this figure. A hydrogen atom has 1 proton and 1 electron. And if you lose that 1 electron, then you have what's called a hydrogen atom. There's only the proton left. That proton has a positive charge, right? And so because of that, this hydrogen ion is denoted as H+, and it's got a positive charge to it. Now, within an element, the number of neutrons in the nucleus can vary. And this is what's called an isotope. So in the first example, we varied the number of electrons to create an ion. In this example, we're varying the number of neutrons in order to create a hydrogen isotope. This is a different meaning than an ion. Isotopes refer to an element that has the same number of protons but a varying number of neutrons. That's another way to put it. So in this case, and hydrogen is the only one that works this way because it's so tiny, where if you add 1 neutron to the nucleus, you actually end up with an isotope, okay? So this is actually called H2. Now, isotopes have special notations which indicate their atomic mass. And in order to create those notations, all you do is add up all the nucleic particles in order to get the isotope number. So H2 has 2 particles in its nucleus, okay? So if that was tough to understand, we're going to go through a few more examples, and hopefully by sort of getting some repetition on this, we'll have a better understanding. So now we've talked about this a bunch. Here's the periodic table, okay? So again, you've got your mass numbers here. Hydrogen has 1, helium is 2, lithium 3, et cetera, et cetera. This is a section over here with carbon, nitrogen, and oxygen that we've also talked about. And so what I want you to realize is that these numbers actually have meaning, right? These numbers are in reference to the number of protons in a nucleus. Okay, and so with the periodic table, you can actually ask and understand a lot about each one of the sort of ionic or isotopic variances that an atom of a particular element can take. And what by that I mean, you can answer questions like these here. And I expect you to be able to do this for this class. And this is as deep as we'll go into the periodic table, but these are basics, right? So, for example, how many protons does hydrogen have in its stable form? I could ask you that question, and all you'd have to do is go look at the mass number, and you say, okay, 1 means that it has 1 proton. Hydrogen has 1 proton. How many neutrons does C means carbon, have in its stable form? You go over to carbon here, C6. You know that in a stable element, neutrons and protons are evenly counted, or they're matched. There's the same number. And so in its stable form, since carbon's mass number is 6, then you know that it's going to have 6 neutrons as well as 6 protons, okay? I could ask you something like, which element has 11 protons? And you know that these mass numbers on the periodic table come from the amount of protons in the nucleus. And so all you'd have to do is go down and find number 11. Na is sodium, right? So sodium has 11 protons in its stable form. Now, going to this topic of isotopes, what is it called when a sodium atom has 12 neutrons? So we know sodium should have 11 neutrons, right? But if it has an extra one, what is that called? It's called an isotope, right? A sodium isotope. And you would add the total number of nucleic particles, 11 protons, 12 neutrons, to get a, what would that be? Sodium 23, sodium 23, okay? So that's the level of familiarity I expect you to have with the periodic table for this course. So you need to know isotopes, you need to know ions. I didn't ask you any questions on ions in the last slide, but you should be able to also interact with electrons in the same way by referencing the periodic table and giving me answers to simple chemistry questions like that. Okay, so we've talked about isotopes and ions. Now we're going to go back and kind of relate this to this concept we've been talking about of nuclear meltdown and radioactivity, radioisotopes, radiation. These are buzzwords that you've probably heard. I'm sure you've heard them, but I want you to be able to actually interact with those words and know what they mean, okay? So isotopes, we just talked about a sodium isotope, for example. They tend to be radioactive. And what that means is that they will actually decay and change their identity by emitting subatomic particles in high energy radiation. Okay, so in other words, that extra neutron in the nucleus makes that element unstable at that point. It doesn't want to have that situation, and so it will actually eject those subatomic particles, and that ejection of those subatomic particles is associated with a lot of energy release, and that energy can actually cause problems. So the actual release of those subatomic particles, that's what is called radiation, okay? So that's radiation, whereas an isotope with that property is called a radioisotope, okay? So radioisotopes are what do damage when they enter bodies of living organisms like us through eating or breathing, and especially when they happen at a high concentration. So after Fukushima, scientists began regularly testing food and water for radioisotopes to see how dangerous, the environment had become. So radioisotopes, we just talked about adding one proton, for example, but you can add many more than that, and have many different types of radioisotopes. And essentially, they'll continue to decay until you get smaller and smaller radioisotopes until you get to that most stable form. Now, elements in nature, carbon, for example, has some amount of isotopes. There's some amount of isotopic frequency, okay? And this can be harmful if you engage or are engaged in an environment with too much of these isotopic particles. But for the most part, they happen at some frequency that your body's capable of sort of dealing with. And so this all leads us to the point that we need a way to measure this. We need a way to measure how radioactive, or the rate at which decay occurs. And we refer to this metric as a half-life. So an isotope's half-life indicates the amount of time it takes for half of its isotopic atoms to decay to that stable form. So for example, cesium is a radioisotope found in the ocean after nuclear accidents or after nuclear testing. You've all seen those mushroom clouds tested in the ocean. And that cesium radioisotope has a half-life of about 30 years. So those isotopes will decay down to the stable form. Half of that population of those isotopes will decay to the stable form within about 30 years of being created. Okay, and so that's just a metric of how fast and how dangerous those types of radioactive particles can be. And it becomes relevant to both science and to human health and ecology. Okay, so we've talked about atoms and gaining and losing electrons becoming charged, and we talked about ions. So the charge of an ion indicates how its electrons have been affected. So for example, a calcium 2+ has lost 2 of its electrons. We've kind of touched on that a little bit. But the point of bringing it back up again here is that radiation energy emitted by radioisotopes is called ionizing radiation, because it generates ions like these, this calcium 2+ when it hits molecules. So if you eat a radioactive molecule because you lived near nuclear fallout, that radioisotope is going to decay, shoot off some of its subatomic particles, and potentially interact with stuff in your cells or in your body, creating ions. And when it when it damages DNA directly, when it creates uh, ionic DNA particles, your cell has to repair that. And if it does that incorrectly, that's what essentially leads to cancer. Or if it does that too intensely, it can damage cells and destroy them altogether. And if it's a really, really bad situation, it will be so detrimental that you could actually die from acute exposure. And so I've gone over a lot of this stuff somewhat quickly, and I'm going to turn it over to a TED video now because they're so eloquently put together. And the key points I want you to take away from this TED Talk is that when a radioactive particle gets inside of your body, it can create DNA damage due to ionizing radiation, and that your body naturally fights this, but acute exposures can create dysfunction. So I'm going to take us to this YouTube link. We'll watch this TED video. We'll talk about these salad photos in a second here. Shut myself.
When we hear the word radiation, it's tempting to picture huge explosions and frightening mutations. But that's not the full story. Radiation also applies to rainbows and a doctor examining an X-ray. So what is radiation really, and how much should we worry about its effects? The answer begins with understanding that the word radiation describes two very different scientific phenomena: electromagnetic radiation and nuclear radiation. Electromagnetic radiation is pure energy consisting of interacting electrical and magnetic waves oscillating through space. As these waves oscillate faster, they scale up in energy. At the lower end of the spectrum, there's radio, infrared, and visible light. At the higher end are ultraviolet, X-ray, and gamma rays. Modern society is shaped by sending and detecting electromagnetic radiation. We might download an email to our phone via radio waves to open an image of an X-ray print, which we can see because our screen emits visible light. Nuclear radiation, on the other hand, originates in the atomic nucleus, where protons repel each other due to their mutually positive charges. A phenomenon known as the strong nuclear force struggles to overcome this repulsion and keep the nucleus intact. However, some combinations of protons and neutrons, known as isotopes, remain unstable or radioactive. They will randomly eject matter and/or energy, known as nuclear radiation, to achieve greater stability. Nuclear radiation comes from natural sources like radon, a gas which seeps up from the ground. We also refine naturally occurring radioactive ores to fuel nuclear power plants. Even bananas contain trace amounts of a radioactive potassium isotope. So if we live in a world of radiation, how can we escape its dangerous effects? To start, not all radiation is hazardous. Radiation becomes risky when it rips atoms' electrons away upon impact, a process that can damage DNA. This is known as ionizing radiation, because an atom that has lost or gained electrons is called an ion. All nuclear radiation is ionizing, while only the highest energy electromagnetic radiation is. That includes gamma rays, X-rays, and the high energy end of ultraviolet. That's why, as an extra precaution during X-rays, doctors shield body parts they don't need to examine, and why beachgoers use sunscreen. In comparison, cell phones and microwaves operate at the lower end of the spectrum, so there is no risk of ionizing radiation from their use. The biggest health risk occurs when lots of ionizing radiation hits us in a short time period, also known as an acute exposure. Acute exposures overwhelm the body's natural ability to repair the damage. This can trigger cancers, cellular dysfunction, and potentially even death. Fortunately, acute exposures are rare, but we are exposed daily to lower levels of ionizing radiation from both natural and man-made sources. Scientists have a harder time quantifying these risks. Your body often repairs damage from small amounts of ionizing radiation, and if it can't, the results of damage may not manifest for a decade or more. One way scientists compare ionizing radiation exposure is a unit called the sievert. An acute exposure to 1 sievert will probably cause nausea within hours, and 4 sieverts could be fatal. However, our normal daily exposures are far lower. The average person receives 6.2 millisieverts of radiation from all sources annually, around a third due to radon. At only 5 microsieverts each, you'd need to get more than 1,200 dental x-rays to rack up your annual dosage. And remember that banana? If you could absorb all the banana's radiation, you'd need around 170 a day to hit your annual dosage. We live in a world of radiation. However, much of that radiation is non-ionizing. For the remainder that is ionizing, our exposures are usually low, and choices like getting your home tested for radon and wearing sunscreen can help reduce the associated health risks. Marie Curie, one of the early radiation pioneers, summed up the challenge as follows: "Nothing in life is to be feared. It is only to be understood. Now is the time to understand more so that we may fear less."
Okay, put on a jacket because it's cold in here. But that is a really great summary using a lot of the vocab that we just went over in the class. And I got to give a shout out again to Marie Curie. She is a total badass in the science world. She discovered radium and polonium, which had a huge impact in sort of this scientific field. And a lot of her work sort of set the groundwork for cancer medicine and different cancer therapies. She's the only person to win a Nobel twice, each time in a different field. So very influential and important woman. Okay, so we've covered atoms, elements, and sort of how these things can be arranged within that context. But how is matter actually put together? So we've talked about the sort of the very, very basic elements of a building system, but how do we actually get to the point where you and I sort of exist? So from that, with that question in mind, we need to go into this field of molecules and start talking about molecules. So when two or more atoms combine, it's called a molecule. Molecules are combinations that are of two or more atoms that are chemically bonded, such as O2. So one oxygen atom is just O, but when two come together, that's a molecule now. Okay, so that's O2. If the molecule is made of two or more different elements, that's when we call it a compound. So water is a compound, H2O. Carbon dioxide is a compound, 1 carbon, 2 oxygens. Okay, and there's this question out there of why do things stick together, right? So why does CO2 want to stay together? Why does oxygen want to hang out with 2 hydrogens? And the answer to this is because they have attraction for the charges. Specifically, protons and electrons are attracted to each other. So this is one of the most famous memes out there, but this is perfect, right? Protons are really attracted to electrons and vice versa, whereas neutrons have a neutral charge, okay? So we've kind of gone over this, but the point is that protons have a certain amount of what we call electronegativity, and that's the tendency of this proton or this an atom in particular to attract electrons. And when they attract electrons, different bonds can be formed. And so we're going to be talking about a couple of different bonds now. Covalent bonds form when electrons are shared between atoms. Okay, over here I've got a water molecule. This red blob is oxygen. Gray denotes hydrogen, and these water molecules represent covalent bonds. And so in a covalent bond, the oxygen molecule which looking down here has how many protons? We know from the periodic table that it has 8 protons. That means it's got 8 positive charges that are all looking for 8 negative charges, right? 8 electrons. Hydrogen, on the other hand, has 1 proton. It's only got 1 positive charge looking for 1 negative charge. And so the electronegativity of the oxygen is much greater than the electronegativity of hydrogen, okay? And so because of this difference, a couple of things happen. Number one, the water molecule actually gets bent, physically bent into a V form like this. And it also creates what we call poles, and these are oppositely charged. So oxygen is going to create more of an attraction for those electrons than the hydrogen, and the oxygen molecule is going to have a negative sort of pole or a negative charge on this side of the molecule, whereas the hydrogen, having less ability to attract those negative electrons, is going to tend towards having a slightly positive charge on each of the other hydrogen atoms. And so these are called poles. So covalent bonds are happening here. They're sharing electrons, but they're not sharing equally, okay? And it creates these poles. Now, when you have many water molecules linking together, you end up with this other type of bond called a hydrogen bond. And a hydrogen bond is when these semi-polar states, this negative charge here and this slightly positive charge here, are interacting with each other, okay? So the charged ends of water molecules attract each other. They form a weak interaction called hydrogen bonds. A lot of times hydrogen bonds are denoted by these little dashes just for notation. But the point is that covalent bonds present in each water molecule are much, much stronger than these hydrogen bonds, up to 10 times stronger, actually. So these are a couple of types of bonds. This is one way that compounds can start sticking together. If the strength of attraction within a molecule is sufficiently unequal, so if the one molecule is so electronegative in comparison to the other one, that it will actually take atoms from the other, take electrons from the other, this is called an ionic bond. So when you create oppositely charged ions of elements, they can attract each other, forming ionic bonds. Table salt is the classic NaCl, right? That's a classic ionic bond where the chlorine atom is so much more electronegative that it physically takes a electron from the sodium atom, okay? So atoms and molecules can come together in mixtures where they don't really react with each other, and these are called solutions. Salt water is a good example of that. So here's a way to think about ionic and covalent bonds. Remember, ionic bonds are when, for example, the Cl atom, the Cl atom here has actually stolen an electron from this sodium, whereas covalent, you're actually sharing the electrons at some degree. So this covalent bond in water is actually sharing this electron between the hydrogen and oxygen, okay? So that's a way to think about ionic versus covalent bonds. Now, before this slide freaks you out too much, don't worry, I'm not going to have you drawing organic molecules here, but I do want to sort of introduce this type of nomenclature to you, or I want to show you this and reduce any fears that you might have about these types of drawings, because it's actually pretty simple. These drawings here are organic compounds, and organic in chemistry means carbon-based. Okay, so organic denotes that there is carbon in that molecule, as opposed to organic food or something like that, which has a whole different meaning, right? So in chemistry, organic means carbon. And one important class of organic compounds is the hydrocarbons. These are all hydrocarbons. You can see hydrogen attached to carbons. And these are really heavily present in petroleum products, plastics, fossil fuels. And so all that you're looking at here is carbon interacting with hydrogen. And so you can imagine that one way to draw these molecules on paper is by just drawing these connections with lines here, okay? So this is one way to represent molecules. This style, most people don't draw this all the way out, but this is another way to represent molecular interactions. This is another way. But the point is, going back to the current slide, that there are many ways to sort of draw chemistry, and they're just easier depending on the application. So don't be freaked out when you see something like this. It's the same thing as those fun little like bubbly cartoons that you see to describe chemistry. Okay, so we've gone over a bit of chemistry at this point, and we know how things want to start to stick together due to those electronegative tendencies. But how are living things, things like us, plants, animals, your dog, your cat, how are we put together? Organisms are put together primarily through macromolecules. And these are the building blocks of life, okay? So macromolecules are just molecules that are big. I mean, macro is big. It's pretty simple, right? So, for example, a water molecule is only 3 atoms, whereas a protein can have thousands and thousands of atoms. And macromolecules tend to fall into these categories of polymers. They don't need to, but a lot of the ones that are biologically important, a lot of the biologically important macromolecules are called polymers. And now polymers are just long chains of repeated molecules. So breaking this word down, poly means many. Mer is a chemistry word for thing, so a polymer is just many units or many things. All right, so polymers and lipids are referred to as macromolecules because they're so large. Proteins, so putting this all together in a good sentence for this is, proteins are polymers made of amino acids. So proteins are a macromolecule. They're big molecules usually. They're polymers, meaning there's many chains of something. And that thing that building block is an amino acid. Okay, so proteins are a macromolecule that's really, really important. Proteins do stuff. Okay, proteins are what make you work. Proteins essentially help chemical reactions occur in your body. They're in your skin, your hair, your muscles, your immune system. It's basically what you are made of. It's the chemistry set that your body has. So proteins do stuff. If you only remember one thing from this slide, I want you to remember that proteins do stuff, okay? So putting this into sort of picture form here, here's a molecule of water. We talked about that. And then here's increasing size of molecules. So here's still a fairly small molecule. This is aspirin. Now here are progressively larger proteins. This one has 7 amino acids. So amino acids have multiple elements in them each. So already we're talking about a larger scale. 7 amino acids, 26, 60. Here's an antibody, anti-HIV antibody, that has thousands and thousands of amino acids. So you can see that there's a vast difference between things that are functioning in your body, these macromolecules that are doing stuff, the proteins, for example, that are doing stuff in your body, versus the molecule of water, for example. Okay. So another type of macromolecule, we've talked about proteins briefly. Another type is called a nucleic acid. And I'm sure you're familiar to some level with DNA and RNA. These are the hereditary sort of carriers. These are the hereditary macromolecules in your body. These contain the blueprints for producing all of the proteins that do stuff, okay? So nucleic acid are polymers, and the mer, the many of the thing in the nucleic acid, is a nucleotide. So macromolecules that are polymers of nucleotides, okay? So regions of DNA that encode for a specific protein, like my brown hair gene or your eye color gene, those are regions of DNA that contain specific instructions for proteins that do stuff. In this case, the stuff is producing brown hair or whatever it is, okay? So in biology, there's this concept of, this is actually called the central dogma. You don't need to remember that, but the point is that DNA tends to produce RNA, which then tends to produce proteins. And again, proteins do stuff, okay? So what we've done with this slide here is gone from this concept of chemistry and chemicals or molecules and gotten all the way to the point where we see how stuff is done in a body, okay? Quickly, you don't need to remember the details of how nucleotides are made, but nucleotides look like this. They have a phosphate group, a sugar, and a nitrogenous base, and we refer to them as A, T, C's, and G's. And so this figure here shows a macromolecule of DNA, a polymer of many nucleic acids, okay? And you know, you're all familiar with DNA being a double helix. So this has really gotten us from chemistry concepts and sort of the periodic table where we started all the way to stuff happening in a body. Other things that are important, other macromolecules that are important and are important building blocks include carbohydrates, which are things that you might find, you know, glucose, like for example, in the bread that you might eat at a meal. So the sugars that are there, the carbs that you're eating. Cellulose, which plants make, those are a type of carbohydrate. And chitin, which make up insect bodies. And these are all carbohydrates. We've gone over this. Central to this is carbon, carbo, and then they're hydrated with hydrogens, so carbohydrates. Okay, so if you just make various arrangements of only carbon and hydrogen, you can get all kinds of stuff, including the sugar in your bread, the lettuce on your plate, or the shell of a bug. Pretty amazing the variety of functions and building blocks that carbohydrates make. And then the last macromolecule we'll talk about for now is the lipids. So lipids they're defined as molecules that do not dissolve in water. These include fats, waxes, and steroids. And so, for example, on this sort of theme of food here, you can see that oil, which is a lipid, doesn't dissolve in the vinegar if you do like a oil and vinegar bread dip or something like that. So again, the reason I'm telling you this is that lipids are defined as molecules that don't dissolve in water. Okay, so we're going to switch topics. We've talked a little bit about macromolecules. Now we're going to talk about something else that's important that will come up again and again in this course, and that's the concept of acidity. Hydrogen ions determine acidity, okay? So in any aqueous, which means just water-based solution, a small number of water molecules split into hydrogen ions, H+. You know, it's an ion because we see this plus, right? It's got a charge. And hydroxide ions, OH-. So H+, OH-. Okay? So pure water contains perfectly equal concentration of these two ions, and therefore it's considered neutral. And if you tip the scale in any direction towards positive or negative, so if you have more H+ than you have OH-, then you start getting into various types of solutions. Acidic solutions have higher concentrations of hydrogen ions, so these plus charges, whereas basic solutions or alkaline have higher concentrations of hydroxide solutions. Okay, and so this scale here is called the pH scale, and it quantifies either acidity or alkalinity of a solution. Okay, so pure water, like we talked about, has an H+ concentration of 10 to the -7, which means basically that it has a pH of 7. Okay, so this is neutral. I don't need you to remember how many there are, but know that pH of 7 is neutral. Acids have a pH below 7, whereas bases have a pH above 7. Now, what's interesting about the pH scale is that it's logarithmic, which means that a pH of 8 is a 10-fold change in the, in this case, the OH- concentration. So each one of these is 10 times as severe as the previous one in terms of the number of OH in the basic category or H+ in the acid category, which look at where stomach acid sits at 1.5. That's pretty freaking crazy. There's not that much stuff in the world that's more acidic. It's, 6.5 times, no, what would that be? 650 times more acidic than water. So pretty interesting. Okay. This is just a tip for you guys. This is how I remember what's basic versus acidic in terms of the pH scale. I think of the base of a pyramid as being wider. So if this width is 14, the base, 14 units long, then acid would only, the most severe acids would be at the top at 0. So for me, I just remember bigger numbers as sort of being the base of a pyramid. This may or may not help you think about how to remember pH. So why is acidity important? Because the amount of ions present in a solution, like blood or water in your body, will affect what gets made and broken down. So we already talked about ions sort of, in the context of radiation, starting to do stuff and starting to interact potentially negatively in that case. But ions want to start to interact with things. Those positive or negative charges want to start finding solutions or configurations with other oppositely charged stuff. And that's what chemistry is chemical reactions like that. Okay, so organic molecules, especially proteins and enzymes, will only work within a certain range of acidity. So if there's too many hydrogen H pluses rolling around, or if there's too many OH minuses, the chemical reactions that they want to perform, the proteins that do stuff in your body, will stop working. Okay, so you don't need to remember this figure, but I do think it sort of creates a good sort of framework that in an acidic environment, these acids, so here's acetic acid, will interact with water to create acetate and hydronium. Here in a basic environment, ammonia and water will interact to create ammonium and hydroxide. And so these different conditions will encourage these chemical reactions, right? So these are just sort of ways to start thinking about why acidity is important. In a basic scenario, in a base situation, a situation where alkalinity is high, maybe these acidic reactions don't occur, okay? And vice versa. And so keeping that balance is critical for things that are living. All right, I'm gonna skip over review questions. Go for those. Look at the general concepts here that I've made you, and know how to answer those questions and these general concepts. I'm going to skip on to the next section here. So we've got a general understanding of how matter is organized and how things like plants and animals are made, and we know that proteins do stuff, but how does stuff actually happen? How is protein A interacting with compound B, right? The answer to that is energy. And so in order to start talking about energy, we need to just define it and have some basic definitions. So energy is the capacity to change the position, composition, or temperature of matter, of stuff. Okay, so when energy causes an object to move, it's a force that can accomplish work. And so you might think about this as like pushing a rock up a hill or something like that. But if you think about it on a chemical level, when we're talking about it at a molecular scale, proteins are also doing work, okay? Now, energy comes in several different forms. Potential energy and kinetic energy. You maybe have heard of these before. This meme is a great example of which one, potential energy or kinetic energy. I would argue that there's a lot of potential energy here. So potential energy is the energy position or composition. So for example, river water held behind a dam contains a lot of potential energy. This duck sitting here contains a ton of potential energy because it could fall over. So the energy potential that this duck has sitting on the very edge of this dam is very high. As soon as that duck falls over that edge, or as soon as the river water rushing through this dam that we're talking about starts to move, that's kinetic energy. That's the energy of motion, the energy of movement. And you can convert energy back and forth between these two forms, okay? So energy conversions take place wherever chemical bonds are broken down or formed also. So we went from a large scale example of a dam or that duck, for example, but now we're talking about it in terms of what you're actually eating and what you're putting into your body. So converting molecules with high energy bonds like glucose, like that bread that we talked about, to low energy bonds such as carbon dioxide, that releases kinetic energy. So you eat food, it gives you energy stores that, in your fat, for example, and then transferring that to movement is a transfer of potential to kinetic energy. When you burn fat via, in this case, rollerblading, that's a transfer of potential to kinetic energy. This can also be seen, you can break it down to the actual interaction happening of molecules of converting sugar and oxygen into carbon dioxide, water, and heat. And this is literally what's happening when you start to exercise, for example, or when you use that food that you've eaten. So potential energy to kinetic energy, that's an energy conversion. So this brings us to some thermodynamic laws, and you may have heard these as well. The first law of thermodynamics is that energy can change from one form to another, but it cannot be created or destroyed, okay? Now, that's the first law. Energy does tend to want to change from more ordered to less ordered. And this is the second law of thermodynamics. And this tendency toward a less ordered state is called entropy. So if you look at this desk here, this is a low entropy system. This is a high entropy system, right? More order, less order. And these are the first and second laws of thermodynamics. So can't create or destroy energy, first law. Tendency towards chaos or entropy, second law, okay? So, for example, a log of firewood is highly organized and it's structurally complex, contains a lot of useful potential energy. And that potential is just in the actual bonds of all the carbon molecules that are and other stuff that are sitting locked in that woody cellular matrix, okay? But when you burn firewood, carbon dioxide, water, and heat is released, and light, okay? The ash and all of these things have less structure and less useful, quote unquote, useful energy. So here you go. Rephrasing this using this figure. Potential energy directly to kinetic energy and a total increase in entropy. Now these logs that used to be contained in this very highly ordered structured system are all out into the atmosphere, okay? All of the molecules, maybe some ash and stuff is left over, but you don't have this organized structure anymore. This system is now highly entropic. Okay, so, but wait, the energy on the planet must come from somewhere, right? That the answer to where that comes from, where that energy comes from is the sun, all right? Light is what powers our planet. The sun releases energy across a huge range of the electromagnetic spectrum. That TED Talk touched on it, briefly, but a lot of it's filtered out by the atmosphere, and we can only see this very, very narrow range of visible light. Okay, so this is the electromagnetic spectrum, and the sun produces this energy, and that's what really drives this planet. Organisms called autotrophs use this sun radiation, the solar radiation, to produce their own food. So in biology, auto means self, troph means nourishment. So an autotroph is self-nourishing. And so this might start to sound familiar if you think of, what is self-nourishing in the world? Photosynthesizing organisms, right? Your plants, your photosynthetic algae, for example. So autotrophs use this process, photosynthesis, which I'm sure you've heard of as well, to transform molecules with low energy bonds, water and carbon dioxide, into sugar molecules with high energy bonds. Okay, so they're going from a more increased entropic state. Entropy is higher in these low energy bonds, and they're creating this low entropy state, this high energy, high potential energy, high order, high potential energy thing that we actually call sugar. Okay, so we'll get into the equation in a second, But I want to go over photosynthesis in general. Photosynthesis occurs within cell organelles called chloroplasts in a plant. And a pigment called chlorophyll is essentially what harnesses light energy. Now, I don't need you to remember the ATP to NADPH, Calvin cycle, any of this, the detail. But what I do want you to know is that light energy interacts with water, and through the process of photosynthesis, what you end up with is sugars and oxygen as an output. Okay, so light reactions split water molecules into hydrogen ions, H+, oxygen molecules, and they produce high energy molecules called ATP and NADPH. The Calvin cycle essentially uses these high energy molecules to form sugars. Okay, so again, this is a helpful figure to look at. I think it's fun to sort of think about how this actually works. It gets way more detailed if you want to start Googling it. But what I do want you to know is this overall process of photosynthesis, okay? So 6 carbon dioxide molecules plus 6 water molecules plus the sun's energy creates sugar and oxygen. So the number before each molecule in the formula indicates how many of those molecules are involved. So 6 and 6, for example. And there's an equal number of atoms on each side of this reaction, right? So what I'm saying is that all of the carbons here are accounted for here, right? All of the oxygens between water and carbon dioxide on this side of the equation are accounted for here. So you haven't added anything, you've just rearranged how this thing, how these molecules look. And you've done that via the sun's energy. So plants take in water through their roots, they absorb carbon dioxide through the air, and then harness the power of sunlight to generate sugar and oxygen. So sugar, just to reiterate, is this molecule here, okay? So this is a critical thing that I want you to remember. The photosynthetic equation, plants use it to create sugar from gas in the air, okay? So I guarantee you I'll ask you a question of, where does the carbon come from in the plant, right? So like the plant that you see growing in your front yard right now, that material is literally pulled out of the air from the carbon dioxide in the air. It's taking that gaseous form using energy to create structure, okay? So to be totally clear, plants create sugar by taking carbon from the air. Roots don't feed on the ground, for example. So next time you eat a donut or have something sweet, you can thank a plant for taking that gas out of the air, creating that sugar that you're now eating in a highly processed form, if in the case of you eating a donut, right? So, okay, so this is one direction. Photosynthesis is one direction, but we also break that sugar down, simply to create water, to create movement, and and create all kinds of other biological reaction. And this overall reaction is called cellular respiration, and it's the exact opposite of photosynthesis. So literally, the arrow, switching the direction of the arrow to go from sugar plus oxygen to create carbon dioxide and water, is called cellular respiration. The energy released is only about 2/3 of the input from photosynthesis. So in other words, think about it this way. What would happen if the sun went out? Would the planet be able to survive? The answer, of course, is no, because the amount of energy that the sun puts into this and the amount of energy that that cellular respiration utilizes and releases is a diminishing amount of return, right? So we need constant input from the sun in order for this planet to survive, okay? So cell respiration occurs in all living things, and that includes plants, okay? That includes autotrophs, but it also happens in heterotrophs. Hetero means diverse. Remember, troph means nutrients. So diverse nutrients. You and I are heterotrophs. We eat all kinds of things. We're capable of eating meat and other stuff, but we don't create our own nutrients. So we're heterotrophs. So cell respiration occurs in all living things, autotrophs and heterotrophs. So I don't want you to come away from this lecture with the notion that for some reason plants don't perform cellular respiration. They do, they just perform photosynthesis at a rate that's higher than the rate of cellular respiration, and therefore the net product of a plant is O2 output, okay? Okay, so notice anything. Photosynthesis and cellular respiration are simply reverse processes. I've just given you a slide with both equations right there, and they've just been flipped essentially for simplicity's sake. And again, plants also perform cellular respiration, but their net output is sugar and oxygen. Okay, review questions, skipping over those. Basic concepts, go look at those. Now we're going to wrap this lecture up with some geological principles. And we're going to talk about, we've talked about all the way from subatomic particles to how things start to do stuff, including movement. And now we're talking about things in the context of the biosphere. So geology is the study of Earth's physical features, processes, and history, and they shape the landscape. They give us the terrain that we daily interact with, and they provide sources like metals and fossil fuels. Okay, so we've learned about how matter works, how living things are organized, how energy gets transferred, how does the planet work. At the Earth's center is a dense core made of solid iron, at the center surrounded by molten iron, and the core is surrounded by a thick layer of less dense elastic rock called mantle. Okay, and the mantle is probably what you're most familiar with. The asthenosphere is an area of upper rock or upper mantle with soft rock, and that's in this zone here, whereas the lithosphere contains the uppermost part of the mantle, and up here is what we actually interact with. You're standing on the crust and the lithosphere. Now, heat from the Earth, from the center of the Earth, drives loops in convection currents that cycle material upward and downward, and this happens on absolutely mind-bogglingly long time scales, geologic time scales. And the idea of these sort of convection currents that are constantly cycling these plates is called plate tectonics. Okay, and we know, for example, that the Earth used to have this massive continental system called Pangaea, where things were much closer together. There's all kinds of evidence for this, including fossil records where you can tell that the Eastern South American fossils are very, very similar to the Western African fossils. So there's lots of evidence that Pangaea used to be sort of the terra firma state of the planet, and they've since drifted apart. So at divergent plate boundaries, and when I talk about a plate boundary, I'm talking about where plates are touching. Plates are moving apart, okay, as magma rises to the surface and cools. At transform plate boundaries, plates slip and grind alongside each other, and that causes earthquakes, okay? So here are divergent plate boundaries. Here's a transform plate boundary, and here's a convergent plate boundary. Okay, so we in California, in Southern California, have a transform plate boundary right outside our doorstep. This is the San Andreas Fault, and it runs the entirety or at least the vast majority of our state. Okay, and you can see this from the air, and these plates are actually moving side to side to each other and create a lot of the earthquakes that we're all somewhat familiar with if you've been a long-term resident. So two possible actions might occur at convergent plate boundaries. Oceanic crust, which is more dense than continental crust, will drive downward in a process called subduction. And the other option is that two continental plates can crush, bend, and buckle, creating mountain range. And this is called a continental collision. So these are these two scenarios here, if we go back a couple of slides. So here's subduction, and then here's collision mountains. So the Rocky Mountains in the center of our continent are a good example of this second example. So tectonics produce what we interact with, Earth's landforms. Plate tectonics build mountains, they shape oceans, islands, continents, and the topography is created by plate tectonics, and these tectonics influence climate and the distribution of biomes. Okay, and so biomes are major habitat types: forests, tundras, deserts, etc. We're going to go over biomes in a different lecture more deeply. For now, I want to talk about the rock cycle. And I've mentioned that cycling is going to be a consistent theme in this class. The rock cycle is one of these cycles of stuff that the planet is constantly doing. A rock is any solid aggregation of minerals, and a mineral is any naturally occurring solid element or inorganic compound with a crystal structure. Okay, they have distinct chemical properties, but the point is, and here are some of them: quartz, topaz, diamonds. These are some examples of minerals. The point is that they break down and reassemble in a process called the rock cycle. And I'm not going to test you on specifics of the rock cycle, but here it is for you. I want you to understand that things, the rocks in this planet go from magma and lava to igneous rock to sediments to sedimentary rock and metamorphic rock. And there's various paths, but the point is that it's always at geologic timescales recycling. Now, this cycling does create a huge diversity of rock types. When magma cools slowly and solidifies beneath the Earth's surface, it forms intrusive igneous rocks. This slow cooling allows this mineralization to occur, creating this multicolored, grainy appearance, like in granite. So if any of you have ever gone rock climbing and gone out to Yosemite, for example, that's an example of the granite that has been cooled slowly under the earth. Magma, on the other hand, that cools quickly forms extrusive igneous rock, and this creates stuff like basalt. So basalt can have these really cool columnar effects and really wild shapes. This one's actually in Japan. As rock weathers from wind, water, particles called sediment come to rest downstream or downwind, and these sediment layers accumulate over time, and they're compacted, and that's what creates sedimentary rock. Okay, so sedimentary rock can be seen in places like Arizona, or actually in PV Cove, Palos Verdes. PV Cove, if you've ever been over there in Los Angeles, has a lot of sedimentary rock as well. Now, geologic forces may bend, uplift, and compress and stretch rock, and sort of like a sculptor with clay, for example. And if the rock's physical property are changed by this, it's called metamorphic rock. Gneiss is a type of metamorphic rock formed originally from granite, and it does kind of look like for example, like a really fancy knife. If you've ever seen a really nice sharp knife that's got those crazy patterns in it, that's made from folding steel, over and over again. Metamorphic rock is essentially the same principle. Okay, so geologic processes occur across deep time. Remember, I keep calling these timescales massive or vast. And geologists have divided the timescale of the Earth's 4.5 billion year history into 3 eras and 11 periods. And the periods are even further subdivided into epochs or epochs. I say epochs, but anyway, the periods are determined by the rock layers, okay, the strata of that rock. And the current period is called the Quaternary period. That began 1.8 million years ago. The current epoch is called the Holocene. And a caveat being that, some people will argue that we're now in a epoch called the Anthropocene, or the human-influenced epoch. But the point is that there are certain sort of markers in geology that you can use to determine and study what was happening at that time. And so some scientists have now called this epoch the Anthropocene. In the last 200 years, soil erosion, atmospheric carbon dioxide, and human population have all grown exponentially. So you can see the erosion rate went up dramatically as soon as essentially humans arrived on the planet. Carbon dioxide, boom, shot way up. Our human population shot way up. On the x-axis here, by the way, you have time. So this is present day, and this is 15,000 years ago. So this is all leaving marks on the planet. And I've actually heard that if you were to, look let's say we go extinct tomorrow, the human population, and you were to look 1,000,000 years into the future, you'd actually find a layer of plastic that had been compressed from our society around the entire planet. So there's some debate about this, but we can pretty much assume that we're now in the Anthropocene epoch. So I'm not going to test you deeply on this last section of geology, but what I do want you to know is that plate tectonics shape the planet. The rock cycle operates on vast timescales. This is the second time that a cycle has come up. The planet has tons of different cycles. We're now in the Anthropocene, but I'm not going to test you on rock types or mineral types, tectonic types, layer types. I think I'm going to go ahead and end the lecture here. You can read these more. There are more slides about earthquakes. California figures prominently in the amount of earthquakes, so go ahead and read through this stuff as well. But I'm going to end the lecture here, having you guys look at the last sort of sections of these. I'm just scaling or going down to this slide here with the concepts. You can read these on your own, but the point is that humans can affect the total risk from natural disasters that can occur on our planet in many ways. But other than this fact, I want you to know that I'm not going to test you on anything from that last section. So go read those slides on your own, but know that the gist is that humans have an effect on natural disasters on the planet. Okay, that ends lecture number 2. I'm going to stop sharing and end the recording.